Thanks for the introduction from Professor Han.
Atmospheric condition using the deep learning method. When we talk about rainfall observation, we usually talk about rain gauges and the weather radar as the method to record rainfall. The rain gauge often offers the high pressure rainfall observation, but at point scale, we often regard it as the ground truth. However, weather radar provides rainfall scans for a large area. The weather radar features a high spatial and temporary resolution, but it also suffers from its relative high uncertainty. The traditional radar data processing flow is shown as below. We put the original radar data into the physical model and processed the ground cluster, signal attenuation, and the beam blockage, and so on. And we processed the data with the statistical model and correction the system error, conditional error, and random error. Finally, we get the radar rainfall products. However, the traditional model ignores the fact that the rainfall observed rain in the air, while a rain gauge measures the rainfall on the ground. This method considers that raindrops fall vertically to the ground and without changing in size. This primacy obviously does not stand because the raindrop's location could change due to the wind drift, and the raindrop size could change due to the evaporation. The atmospheric factors that influence the microphysics processes that act as the raindrops falls include evaporation, wind drift, and so on. For example, the pressure, temperature, and humidity fields could lead to the mass variation of raindrops, and the horizontal or vertical wind could lead to the drift of raindrops. However, it is difficult to depict the variation in raindrop size distribution due to the diversity of atmospheric conditions and their instability. In addition, microphysics processes that occurs raindrops fall are too expensive to simulate. Currently, the deep learning method is playing a critical role in our ability to gain a deep understanding of the behavior of complex geosystems through data-driven discoveries and model-driven insights. Thus, some study has used the deep learning method to discover the complex relationship between radar data and the ground truth rainfall observed by the rain gauge. Therefore, the objective of our study was to explore the impacts of the atmospheric condition on the radar gauge rainfall discrepancy. We call it RGD, and to establish a model to reduce the uncertainty in the radar rainfall estimates using the deep learning method. Secondly, the depth source and the wolf model. Our study area covers most area in the UK, as shown in this figure. Our study data include the original radar rainfall estimation data, which with a resolution of 5 minutes and 1 kilometers, and source from Met Office, and more than 200 the rain gauges data with a resolution of 1 hour, which also sourced from the Met Office. and the ERA interim meteorologic data. We use the WRF model to download ERA data to get 5 kilometer and 1 hour resolution atmospheric fields. We implemented long-term experiments from 2013 to 2017. The WRF simulation was performed using the follow parameters, the Marathon double moment microphysics scheme, the KF cumulus scheme, and the MYJ boundary layer scheme, and so on. We designed the doubly listed domain, the WRF model. The configuration of the domain is shown in this table. Secondly, the methodology. We investigate the correlation between the RGD and the different atmospheric fields from long-term and large spatial scale perspective. The SOROC, Spatial Measuring Correlation Coefficient, was used to evaluate the association between the RGD and the atmospheric fields. And the MAE, mean absolute error, was selected to describe the RGD of each rainfall event. Long short-term memory networks, LSTMs, has excellent ability to learn the long-range dependency of the rain time series data and can solve the regression problem with complex nonlinear relationship between the input and the output values. LSTMs used in this study to determine the complex effects of the meteorologic elements on the descent of the raindrops from the air to the ground by training through the use of a lot of data for historical rainfall events. The LSTM models used in this study include 3 layers. An input layers, which consider radar rainfall and 3-dimensional atmospheric fields at each time step, a hidden layer, and output layers, which consider gauge rainfall at each time steps. We designed 3 RGD adjustment models. Scheme 1, which considers the evaporation. We call it mass variation scheme, MV, which includes the LSTM input layer include the pressure, temperature, and the relative humidity. And scheme 2, the wind drive scheme, which considers the horizontal and vertical wind, and the combined scheme, which consider all the meteorologic fields used in this study. We implemented a 10-flawed cross-validation procedure to prevent the underfitting and overfitting problem. We evaluate the RGD adjustment models use 4 indicators: the mean bias error, MBE, the root mean square error, IMSE, and the Pearson's correlation coefficient, PBMC, and the critical success index, CSI. Then we got results. Firstly, we analyzed the correlations between the RGD and the atmospheric condition. This figure shows that the spatial pattern of the SROC of the MAE between the radar and the gauge rainfall and the different atmospheric variables for hundreds of rainfall events at each study sites. As shown in this figure, most sites exhibit negative correlation between the RGD and the atmospheric pressure or the relative humidity. However, for the remaining atmospheric fields include the temperature and the horizontal or vertical wind speed. Most sites showed positive correlations. This figure shows two ensemble 10-fold cross-validation tests on hidden units and the number of the hidden area of 3 schemes. From this figure, we can get the better or suitable layers and hidden units for each adjustment model as shown in this table. This figure compares the amount of total rainfall over study area between the original and the amended radar images, corresponding to 4 raining days. The amended rain gauge presents a trend that was similar to those of the original images. However, the difference between the original and the amended rain images were also very clear. Then we evaluate the performance of each RGD adjustment models. From the results, all the 3 models all achieved a great performance. Among those schemes, the combined model showed the best performance, followed by the mass variation model, and then the wind drift model. Overall, the combined model could reduce the RMSE between the radar and the gauge rainfall by more than 20%, and increase PPMC from 0.23 to 0.53, and improve the radar rainfall forecast successful rate from 0.56 to 0.92. We also analyze the relationships between the model performance and the atmospheric condition. The relationship between model performance and relative humidity and the wind speed is shown in those 2 figures. From the figures, we can see that the performance of the 3RGD adjustment model increased with increase in relative humidity or wind speed. The RMSE improvement rate ranged from about 17% to 28%, while that of PPMC ranged from about 41% to 96%. Therefore, the proposed RGD adjustment models showed great performance under the high relative humidity and the high wind speed. Finally, we can go those conclusions. Conclusion 1, the relationship between the radar gauge rainfall difference and the atmospheric condition was strong. Conclusion 2, the 3 development RGD adjustment models all achieved a great performance. Conclusion 3, the performance of the RGD adjustment models increased with an increase in the relative humidity and wind speed. Thanks for your attention. Any questions?
Okay, yeah, very interesting presentation. Because the rainfall measurements is quite a challenging task, yeah, especially over cities, because it's not easy to put rain gauges in cities. Yeah, so your work is very useful, for urban resilient studies. Okay, so any questions? We probably got a couple of minutes, yeah? So any questions from the audience? I got a question, yeah?
Okay.
Can you go back to the slides you got? You showed the performance
okay.
improvements with wind. Is that with the wind and the relative humidity? Seems it's getting better when the relative humidity goes up. Yeah, it's near the end. Go further down. There's a
This one.
Is that this one? Performance. Okay. Yeah. So relative humidity goes up. Performance improvements goes up.
Yes.
Why is that? Any reasons?
I think that it's because we consider the evaporation and the wind drift of the evaporation and the wind drift on the radar rainfall estimates. So if the relative humidity is high or wind drift speed is high, our model's performance will be great.
Yeah, but it's partly, if you consider wind, if wind is great, yeah, it's large.
Yeah.
When you consider it, you can improve it. But if relative humidity is high, there will be less evaporation.
Less.
Then performance shouldn't increase. I don't know. It's yeah, if it's very dry air, there will be more evaporation. Yeah, so if you consider the evaporation, you can improve it.
Okay.
But if it's high, there's no evaporation, so the performance should be higher if it's very dry. Yeah.
But our analyzed results show this this results.
Yeah, interesting, but it's just slightly, yeah. But this is machine learning. That's the result. It's similar to another study. I think it's from Professor Huang's team.
Okay.
Shows this the CO2 was higher during the summer, lower in the winter. But we will know photosynthesis is stronger in the summer. Yeah, in the winter there's not much photosynthesis. That's very puzzling as well. Yeah, but if that's the data, so there must be some reason, but I don't know the real reason. But it's certainly against logic, but very interesting. Yeah.
Okay, thank you.
Yeah. Okay. Okay. Any other questions? No. Okay. Thank you, Dr. Yang, for a very interesting presentation. I think it's the radar data should be used more in city resilience study in the future, really. Yeah, because I don't know in China, certainly, yeah, certainly in the UK, it's not easy to put rain gauges in cities. Yeah, think about it. There's so many buildings. Yeah, where do you put a rain gauge? If you put a rain gauge on the top of the building, it's not going to work well. Yeah.
Yeah, we will consider it in the future.
Yeah.
Thank you.
So very good.